In Chapter 4.5, we're going to look at exponential and logarithmic functions and solving for both of these types of equations. Our objectives are solving exponential equations. Our second objective is to solve logarithmic equations. And finally, we're going to use exponential and logarithmic equations in applications. So we're going to look at the equivalency property of exponential expressions. Some exponential equations can be solved using the equivalency property of exponential expressions. In this case, let b, x, and y be real numbers with b greater than 0 and b not equal to 1. Then b raised to the x power equals b to the y power means that x is equal to y. So for example, we have the following equation. We have 5 raised to the 3x minus 1 is equal to 125. To solve this equation, we put everything into base 5. So on this side, we will leave alone. But on the other side, we'll change this to 5 to the third power. Now, based on the equivalency property, we see that 3x minus 1 is equal to 3. 3x is equal to 4, or x is equal to 4/3. So in this particular case, x is equal to 4/3, and when we put that into the equation, we have 5, 3 times 4/3. The 3's cancel, and we're left with 4 minus 1, which is 3. 5 raised to the third power is equal to 125. So again, we're going to solve these equations. Remember, we are going to rewrite everything into a particular base. In this particular case, we're going to go and put 1/4 as 2 raised to the negative 2 power. And then we're going to set this equal to 8 raised, we're going to set this up as 2 raised to the third power raised to the x power. Well, this is just 2 to the minus 2 power is equal to 2 times 3x. And so this means with the equivalency property, we have minus 2 is equal to 3x. We have negative 2/3 is equal to x. And of course, if we put that back into the original equation, it solves the equation. Notice in this case we had to go to a different base. 4 wouldn't work, nor 8 wouldn't work. So in the next problem, we're going to have to do the same thing. I'd like you to pause and see if you can do this particular problem yourself, and then we'll come back and show you the answer. So go ahead and pause. So when we look at this particular problem, we started out and put it into a base 2 format, where we have 2 raised to the third power times x plus 3 is equal to 2 raised to the 2 power times x raised to the 5 minus 2x. We distribute the 3 and we get the following equation. 2 raised to the 3x plus 9 is equal to 2 raised to the 10 minus 4x. And now by the equivalency property, we have that 3x plus 9 is equal to 10 minus 4x. This is a minus sign here. And now when we solve, we get 7x is equal to 1, x is equal to 1/7. And when we put it into our calculator to make sure that this is the right answer, when we do that, we do get the right answer for both sides of the equation. So, solving for exponential equations using logarithms. Most exponential equations cannot be written to have matching bases. To solve this equation, isolate the exponential expression and then take the logarithm of both sides. Then apply the power property of logarithms. Typically, we'll take the common log of both sides or the natural log of both sides. So in this example, we have 2 raised to the x power is equal to 7. There is no base in the world that's going to help us with this particular problem in exponentials to get to the equivalency problem. So we take the logarithm of both sides. When we do that, we have to apply rules of logarithms. So we take the log of 2 raised to the x power is equal to the log of 7. Now what we do is we use the power rule, in this case x log 2 is equal to log 7. So x is equal to log 7 divided by log 2. And of course we can get on our calculator the exact number for this particular problem. And I think it's about 2.8 something, 2.807. Now we can do the same thing with the next problem. Again, this is a very difficult problem unless you use some sort of logarithm. So immediately we can rewrite this using the power rule if we know the power rule. We can say this is a minus 0.02x log of 3. This is a common log of 3 is equal to the log of 0.07. And now we're solving for x. So x is just equal to the log of 0.07 divided by a negative 0.02 times log of 3. Now, of course, if we have our calculator, we can find out what this number is. And I think it's 121.028. So in the next problem, in problem 6, we're going to try to look at an exponential. And so this one will probably use a natural log of both sides. But the first step here is to subtract 4 from both sides. So we get 3e to the 2x is equal to 7. We've subtracted 4 from both sides. Now we divide by 3. E to the 2x is equal to 7/3. Now we can take the logarithm of both sides. So this is 2x natural log of e is equal to the natural log of 7/3. And now we know what log e is, it's just 1. So we just end up with x is equal to the log, the natural log of 7/3 divided by 2. And of course, we again can use our calculator to find an answer for that, but I'll go ahead and leave that for you to discover. So now we have number 7. Again, you want to use the common log since you don't have, or you can use the natural log, but the common log would probably be okay for this particular one. So in this particular case, we can immediately set up 3x minus 2 log 2 is equal to, and this is in parentheses by the way, 2x plus 1 log 3. Now you say, boy, that's going to be difficult, but you're going to distribute the logs through. And what I mean by that is you're going to distribute the log all the way through. So I'm moving all of this over here so I can give you a better feel for that. So we have 3x log 2 minus 2 log 2 is equal to 2x log 3 plus log 3. Now at this point we're going to move all the x's together and then just the regular logs onto the other side. So here we're just going to put in 3x log 2 minus 2x, we're subtracting 2x log 3 from both sides, and then we're going to add 2 logs to both sides, 2 log 2, so we get 2 log 2 plus log 3. Well, we're not done. We can take an x out and we get 3 log 2 minus 2 log 3 is equal to 2 log 2 plus log 3. Now we can divide through by this and we'll get the following. We'll get 2 log 2 plus, and I could do something with the powers here if I wish to do so, but you'll get the idea. We get 3 log 2 minus 2 log 3. And of course we could do some more manipulation. Turns out that this is approximately equal to a negative 21.097. So now we have something in quadratic form. We have e to the 2x minus 8e to the x plus 12 is equal to 0. When we see something like this form, we usually use substitution. So in this particular case, I'm going to let y equal e to the x. And now I'm going to rewrite this equation as y squared minus 8y plus 12 is equal to 0. Now I can solve this by factoring. I have y minus 6, y minus 2 is equal to 0. So this means that y is equal to 6 or y is equal to 2. But now we're going to substitute back in. So this is e to the x is equal to 6, and this is e to the x is equal to 2. This is x is equal to the log of 6, and x is equal to the log of 2. And that's it. Our next concept is solving logarithmic equations. So we're going to talk about the equivalency property of logarithmic expressions. Note the difference between these two equations, the log of 3x minus 4 minus the log of x plus 1 equals log 2. And then the following equation, log base 3 of x plus 6 minus log 3 of x minus 2 is just equal to 2. In the first equation, all terms have logarithm. The second equation is a mix of logarithms and constant terms. These two equations require different styles of solutions, in fact, different methods as well. For solving equations of the first type, we will use the equivalency property of logarithmic expressions. So in other words, let b, x, and y be real numbers with b greater than 0 and b not equal to 1. Then the log base b of x is equal to the log b of y, which means that x equals y. So in our first example of 9, we see that the base log 2 is the same on this side of the equation as it is on the other side of the equation. So now we can use the equivalency property of logarithms, and we know that 5x minus 1 is equal to 2x plus 17. Now we just solve for x, and here we get 3x is equal to 18 and x is equal to 6. And of course, if we put that into the equation, right, into the original equation, we just have the log of 2 of 6 times 5 is 30 minus 1, right, is 29 on this side of the equation. And now if we do it on the other side of the equation, we get the log of 6 times 2, which is 12, plus 17 is 29. Well, those are equivalent statements. Let's look at the next equation, right? We have, I would like you to do this one. You should be able to do this one pretty quickly. You can pause it if you would like. The log of x minus 7 is equal to the log of 5 minus x. So why don't you go ahead and try this one real quickly. Pause it, and we'll come back with the answer in just a second. So here was the solution. We've said x minus 7 is equal to 5 minus x. We combined x's. We have 2x is equal to 12. X is equal to 6. But there's a problem here. When we put this back into the situation, we have log of 6 minus 7 is a minus 1 equals log of a minus 1. What is the problem? Well, you can't have a log of a negative number. Remember, whatever's inside has to be greater than 0. So for example, our domain for the logarithm on the left-hand side is x minus 7 has to be greater than 0. That means that x has to be greater than 7 on that side. And on the other side, it's 5 minus x is greater than 0, which implies that, in fact, x has to be less than 5 on the other side of the equation. So these don't work out because this doesn't work out. So this is a meaningless solution. So now let's look at this solution here. We have the logarithm of 3x minus 4 minus the log of x plus 1 equals log 2. Now everything has the same base, but we have a logarithm minus another logarithm, and we know exactly what to do with that with the rules of logarithms. So here we'll have to rewrite this as the log of, here, let's do this correctly here, the log of 3x minus 4 divided by x plus 1. That is the quotient rule of logarithms, equals log 2. That's our first step here. And now, because we have the logarithm of the same base, we have the equivalency property, which states that 3x minus 4 over x plus 1 is equal to 2. So 3x minus 4 is equal to 2x plus 2, because I'm multiplying through by x plus 1. And now I'll solve for x. I can subtract 2x from both sides. I get an x, and I can add 4 to both sides. I get a 6. So here I have x to this is equal to 6. When I plug this in, I should be okay, because 3 times 6 is 18 minus 4 is 12. So the log of 12 minus the log of 7 is equal to the log of 2. And so that's how this particular problem will work. Or actually it's 14, right? It's not 12. So when we plug this back in fact, let's do that. Let's just plug it back in. Let's get the log of 18 minus 4 is 14, right? Minus log of 7 equals log 2. Well, this is just the log of 14 divided by 7 is equal to log 2. And so log 2 equals log 2. Alrighty. So here again we have a similar problem, except now in this particular case we have a plus rather than a minus, so we will still have to use the rules of logarithm, and when we have a plus we have to use the product rule of logarithms. So it's the log of x plus 3 times x is equal to the log 10. And now we have x squared plus 3x is equal to the log of 10. And so we can use the equivalency property here. We get x squared plus 3x is equal to 10. Oh, this is beginning to look like a, what do we call this? A quadratic. So x squared plus 3x minus 10 is equal to 0. We can factor this. X plus 5, x minus 2 is equal to 0. So this is saying x is equal to a minus 5, or x is equal to 2. The minus 5 is not going to work, because when we put minus 5 in there, we get a log of a negative number. That's not going to work. So now the question is, does the log of 2 work? And it does, because we can plug this back into there. And we see that the log, or natural log of 10, when we put that in, is equal to the log of 10. So the only answer here is x is equal to 2. So again, we have a more complicated scenario here. We're going to go ahead and rewrite this equation. We're going to have log 3 of x squared. That's the power rule of logarithms. And then we're going to have the following. We're going to have the log of 3 of 2 times 3x minus 4. Okay, so now we have log 3 of x squared is equal to log 3 of 6x minus 8. Now, by the equivalency rule, we have x squared is equal to 6x minus 8. We can create a quadratic. We get x squared minus 6x plus 8 is equal to 0. We have x minus 4 and x minus 2 is equal to 0. So this means that x is equal to 4 or x is equal to 2. And in this case, both solutions do work. So sometimes we have mixed problems where we have logarithms and we have exponentials. To solve equations that are mixed of logarithms and constants, we collect all the logarithms together and then rewrite the equation in exponential form. So for example, if we have log b of x is equal to k, then we know immediately that x is equal to b raised to the k, where k is a constant. So now we can look at the first problem, number 14, and we can immediately see that we can rewrite this in the following way. 5 raised to the second power is equal to 3x plus 1. So we have 25 plus minus 1, which is 24, is equal to 3x, and x is equal to 8 in some sense. If we plug that back in to this equation, we get 24 plus 1 is 5, and that's 25. Log 5 of 25 is just the power of 2, so that checks out. Now we're going to do the next problem, but we have to use the law of logarithms in order for this to work out. And in the law, we have to use the fact that we have what's called a quotient rule, and so now we can rewrite this as the log 3 of x plus 6 over x minus 2 is equal to 2, or x plus 6 over x minus 2 is equal to 3 raised to the second power, which is 9. So now we have x plus 6 over x minus 2, which equals 9. We can multiply through by x minus 2. We get x plus 6 is equal to 9x minus 18. And now we can solve for x. We can bring this over. This is going to be 24. is equal to 8x, and x is equal to 3. And this will work because we don't have a negative log of either side. So we would like you to try to solve this particular problem. I would like you to pause the video and solve the equation, and we will come back and show you how this solution works in just a few seconds. So please pause. So in this case, we did it two ways. First of all, we added log x to both sides of the equation, and when we did that, we got the log of x plus 15 plus log x is equal to 2. Then we used the product rule of logarithms. So we have the log of x times x plus 15 is equal to 2. We multiplied out the x's, we expanded it. We get the log of x squared plus 15x is equal to 2. And then we put it into the exponential form, which we can do. And so we get x squared plus 15x equals 10 raised to the 2 power. And then we have x squared plus 15x minus 100 is equal to 0. There's our quadratic. And we can factor that. X plus 20 times x minus 5 equals 0. That shows us that x is equal to 5. But suppose I didn't know how to factor, I can use the quadratic equation. And when I put it back in there, I see that the negative 1 does not work. The negative 20 doesn't work. So we left with x is equal to 10 over 2, which is equal to 5. So here again we have the following equation. We have the log 4 of x squared minus 9 minus 3 is equal to log 4 of x plus 3. We're going to rewrite this in the following fashion. I'm going to write this as log 4 of x squared minus 9 minus log 4 of x plus 3 is equal to 3. I can rewrite this equation into that form. And now I can use the quotient rule for logarithms. So now I have log 4 of x squared minus 9 over x plus 3 is equal to 3. This is the log 4 of x minus 3 times x plus 3 over x plus 3 is equal to 3. Those cancel, so I'm left with log 4 of x minus 3 is equal to 3. And now I can write it in the exponential form. So x minus 3 is equal to 4 raised to the 3rd power. That means that x minus 3 is equal to 64, or x is equal to 67. So there is my answer for this particular problem. So our last objective or concept is to use exponential and logarithmic equations in applications. So if $20,000 is invested in an account earning 2.5% interest compounded continuously, determine how long it will take the money to grow to $45,000. Round to the nearest year. Use the model A is equal to P e to the RT. So in this particular case, we have a principal. So in this case, P is equal to $20,000. R is equal to 0.025. And we don't know what T is. T is our question mark. We're trying to find T. How long does it take? But A, in this particular case, is equal to 45,000. So we'll set it up. 45,000 is equal to 20,000 times e to the 0.025 times t. Well, the first step is to divide 20,000 into 45,000. So here we get 2.25 is equal to e to the 0.025 times t. Now we can take the natural log of both sides. So we get the log of 2.25 is equal to 0.025 times t, the log of e, but that's just 1. So we're left with the log of 2.25 divided by 0.025 is equal to t. So t is approximately equal to 32.437. So the nearest year really is about 32 years. The following formula relates the energy E in joules, the release by an earthquake of magnitude M. The log E is equal to 5.24 plus 1.44 m, where m is greater than 5. What is the energy released by a magnitude 6 and a magnitude 7 earthquake? Well, so we put these into the equation. Log E, we'll just do the first one actually. 6 and 7 follows the same way. 5.24 plus 1.44 times 6. So log E is equal to 13.88, which means that E is just equal to 10 raised to the 13.88, which is approximately 7.586 times 10 to the 13th power. That's quite a release of energy. And then, of course, you can try 7 as well. So here, as comparison in a 1 megaton nuclear weapon, would have an energy release of 4.18 times 10 to the 15th joules, and the eruption of volcano Karatoka in 1883 produced an energy release of 2.9 times 10 to the 19th joules. So in some sense, the volcanic eruption, we can actually try to figure out what the magnitude would be in terms of the of an earthquake, magnitude earthquake. So if we looked at 4.18 times 10 to the 15th, we took the log of that. That was equal to 5 hold on just a second. So it's 5.24 plus 1.44 times m. So this was the 1 megaton nuclear weapon, and so to find m, we will do the following. So when we've set up the equations for both the nuclear weapon, 1 megaton nuclear weapon, and for the volcano, we see that for the nuclear weapon, it would be equivalent to an earthquake with a magnitude of 7.2, whereas for the Krakatoa volcano, it was a 9.778 magnitude of a release of energy for an earthquake. Well, that concludes our chapter 4.5. Please work some of the skill problems in the chapter and work some of the word problems. We'll be talking a little bit about this in class, and we'll do some problems in 4.6, and we'll be done with chapter 4.